This is 5.1/5.2 part 2. If you did not watch part 1, please go back and do so because we talked about Riemann sums. And we saw that when we find the Riemann sum, it did not equal a plus value all the time. So you can have negative or net area. With the definite integral, also, we will get net area. So we can get negative answers for this. And by the way, the definite integral is one of the most important things we can learn in calculus because now this gives us the power to find the area above or below the x-axis of shapes that aren't exactly, what we've learned in geometry thus far. So let's go ahead and look at example number 2. Write the following limit as a definite integral. So the limit as n approaches infinity of the intervals from 1 to n of the cube root of 5 minus x sub I squared delta x on the interval from -1 to 1. Well, if we use the fundamental, we haven't learned the fundamental theorem of calculus yet, but definite integral, then what I'm going to do is I'm going to integrate from that lower limit, which is -1, that is a, to b, which is the upper limit, which is +1. And then we're going to integrate the cube root of 5 minus x squared dx. Okay? So that's what it's going to look like. And by the way, my dog is saying hello to you. Coco, come here. Okay, so for part B, we have the limit as delta x sub I approaches 0, and we're creating intervals from 1 to n of cosine pi x I minus 1 delta x on the interval from 0 to 4. So again, we're going to integrate from 0 to 4 of the function, which is cosine pi x dx. Okay, so again, we're just rewriting these. Now that we have the ability to integrate or use the integral, we don't have to make rectangular regions under the curve anymore. Okay, so this is going to be game changer and it's going to be so much easier as long as you know integration. So make sure you know all those rules that are in the first page of this unit. Okay, so let's look at this next example using areas to evaluate the definite integral. So when the function is greater than 0 from a to b, then the integration from a to b f of x dx equals the area. So what does that mean? That means that if I have the values above the curve, then that area is going to turn out to be naturally positive because it's above the x-axis, okay? When the function is less than 0, I'm looking at this right now, on the interval from a to b, then the integration from a to b f of x dx equals negative area, okay? So what's going to happen is when you integrate values underneath the curve, and I'm going to do this right here. Maybe I should use a different color, green. I guess that didn't help, guys. So, yeah, we'll use pink. That works. So when I'm looking at this over here, so this stuff, I'm underneath the curve, and when I integrate it, it's going to give me a negative number. So to counteract that, because remember, we're trying to find area, we have to have another negative in front of there, because a negative times negative will give me a positive. And that's why it's telling you, like, hey, whatever area you get, put a negative in front of there so it becomes positive. Okay? All right. So before we start using this, we're going to do a geometric areas to evaluate definite integrals. So let's look at 3a together. It says, hey, I want you to find the integral from 0 to 3 of 2x dx. So my function is 2x. My integration is from 0 to 3. Okay, so because it's telling me not to use definite integral or take the integral, I'm going to draw this out. So my function is 2x. And I'm going to make a chart X and then my Y value, okay? Because I want to draw this out. I know it's a line, but I'm just going to humor you guys. So I'm going to plug in 0. So 2 times 0 is 0. I'm plugging in 1. 2 times 1 is 2. I'm plugging in 2. 2 times 2 is 4. And I'm plugging in 3. And 3 times 2 is 6, okay? So I have these points 0, 0, 1, 2, 2, 4, and 3, 6. Now I'm going to graph it because it says use the geometric area to find, or yeah, geographic areas to evaluate this. Okay, so I'm going to put, we're going up to 6 on the y-axis. So I'm just going to go to 6 on each one. Okay, and now I'm plotting points. So 0, 0 is right here. 1, 2 is here. 2, 4 is going to be here. And finally 3, 6 is going to be here. So if I connect all of these, I get this. And if I bring this down, I get a triangle. Okay. So the area that we're looking at in this particular thing is a triangle. Okay, to find the area of a triangle, I take base times height and I divide it by 2. Or you can use 1/2 base times height. Okay, so the base of this triangle, the base is 3 units long. So it's 0 to 3. The height is how tall it is, so we can see it goes up to 6. Okay, so area equals base, which is 3, times height, which is 6, divided by 2. So 18 divided by 2 gives me 9. So the area of this is 9. Okay, so that wasn't too bad. Okay, let's move on. The same directions, use the geometric area. So we have to graph this. Now we have the absolute value minus 2. Just to let you know that, you know, the absolute value function makes a v. And if we take minus 2, that means we've moved it down 2 units, right? So it's going to look like that. But what I'll do is we're going to plot out points. So let's go ahead and do that. So again, let's make a chart. Whoops, let me fix that. That's not too great. All right, so I'm doing 0, 1, 2, and 3. And if you're wondering where I got these values, I'm just using the integration from 0 to 3. So if I plug in 0, I get 0 minus 2, which is negative 2. If I plug in 1, absolute value of 1 is 1 minus 2 is negative 1. If I plug in 2, the absolute value of 2 minus 2 is 0. And if I plug in the absolute value of 3 is 3 minus 2, which is 1. So I get these points 0, negative 2, 1, negative 1, 2, 0, and 3, 1. So let's go ahead and plot that out. So I'm going to go ahead and make a chart here. Okay, and I'm doing 0, 1, 2, 3. I'm just going to go 3 in each direction. Okay, all right, now I'm ready to plot the points. So the first one is x equals 0, y equals negative 2, which makes sense because we had a shift down. The next one is 1, negative 1. The next one is going to be 2, 0, and then finally 3, 1. Okay, so if I connect those up, it looks like this. And if I have to find the geometric area, I'm going to go ahead and draw this out. So basically, I have 2 triangles that I have to find the area for. Okay, I'm going to call this triangle number 1 and triangle number 2, just so we know what's what. Okay, so let's do triangle number 1. If I redraw it, it looks like this. Okay, so the width of it is 2 units, and then the height of it is also 2, even though it says -2. Okay, so we're going to do area equals base times height divided by 2. So area equals 2 times 2 divided by 2. Area equals 4 divided by 2, which is just 2. So the area of the first one is 2. The second one, it's above the x-axis, looks like this. The width of the triangle is 1 unit, and then the height is also 1. Okay, so area equals base times height over 2. The base is 1, the height is 1 divided by 2. So this becomes 1/2 for the second area. So this is area 1, area 2. Okay, so to find the total area, I'm going to add area 1 plus area 2. So area 1, remember, was 2, plus area 2 is 1/2. Okay, so this equals 2.5. That is my total area. Okay, all right. Again, remember, area 1 was the triangle underneath the curve, but I'm trying to find the area of a triangle, so I don't care if it's underneath the curve. I am going to do the height as being positive. Okay, all right. So let's look at the properties here of definite integrals. Given the function f and g are interchangeable, or integral, sorry, on the values from a to b, so we have the integration from a to b of f of x dx. This is equivalent to or equal to the limit as n approaches infinity of the intervals I to n of the function x sub I delta x. So basically, now we don't have to make pictures, we can just integrate, but we have to do so with what's called a definite integral. So the first property, if you're integrating from a to b of a constant times f of x, I can kick the constant out and integrate the function from a to b. Second property, if I am integrating from a to b of the function f of x plus or minus the function g of x, so basically we're talking about polynomial functions, then we can integrate each piece. So the first one, I integrate from a to b of f of x dx plus or minus integration from a to b of g of x dx. 3, if I'm integrating from a to a of f of x dx, that equals 0. Remember, this is giving me area. So this doesn't even make sense because I'm not moving. My values are a to a. So this makes sense that it's 0, not moving from a to a. So I don't have a region to take the area of. Okay? 4, if I'm integrating from a to b of a constant dx, then what you do is you take the constant times the upper limit b minus the lower limit a. 5, if I'm integrating from b to a f of x dx, then I have to fix this, because when I integrate, the larger number has to be the upper limit and the lower number has to be the lower limit. So to fix it, what you do is you put a negative out front here and fix the integration. So b is on top and a is on the bottom. Okay, so you only have to do this when the integration is from b to a instead of from a to b. Okay, all right. So if I have an integration from a to b f of x dx plus the integration from b to c f of x dx, then I can simplify things because I'm taking the area from A to B, B to C, I can just say, hey, find the area from A to C. So if you look at this, I have A to B, right? And then I'm taking the area from B to C. So again, I can just write this out as integration from A to C. Okay, I'm going to stop here and we're going to do a part 3 of the video. Thanks for watching part 2.